The hunt continues for the math behind the computer. We know that sets are a great way to store objects if we don't care about order or repetition. But here we run into an immediate problem. Computers use binary, a bunch of ones and zeros. But if we tried to put that into a set, it would become the set 1, 0. If we only have two numbers, it's going to be quite difficult to run arbitrary code, watch high-quality educational videos, or even play Doom. So let's add a simple rule to sets. Order matters. This simple rule gives us our second mathematical object, the sequence. And oh boy, does it pack a punch. Before diving into the unique abilities of sequences, let's talk about how they're similar to sets. First off, both sequences and sets can either be finite or infinite. Secondly, we can define both sets and sequences directly. So, set 2, 3, 1, or sequence 1, 2, 3. More interestingly, both sets and sequences can be defined by rules. Sets can be defined by the predicate p of x, meanwhile sequences can be defined either explicitly or recursively. An explicit definition of a sequence might be bn equals n squared. So we know that if we're looking at the 12th value in the sequence, the value is 144. A recursive definition is when the nth term is defined by some previous term. For example, a sequence might begin with d of 1 equals 6, d of n equals d of n minus 1 plus 6, where n is greater than 1, giving us the 6 times table into infinity. Also, like sets, sequences are not confined to numbers, but could also be letters, giving us the freedom to create sequences like this. Sequences made of all characters are typically called strings, and even though each character is an element of a sequence, we often write the symbols with no space, so they look like the words we're used to reading. Because sequences have an order, we can distinguish between repeated values. So while the third and fourth characters in freedom are the same value e, we can repeat the value in different locations in the sequence or string. Repeated values mean our computers, instead of being limited by a set of 0 and 1, can instead have sequences of binary, containing as many repeated zeros and ones as their little processors can handle. Sequences and sets are frequently used in tandem. In this video, we're going to discuss a few different topics involving both mathematical structures: strings and regular expressions, characteristic functions, how sets, sequences, and arrays intermingle, and finally, countability and infinity. First, let's define strings a bit more mathematically. Formally, if we have a set of symbols called A, then the set A star can be thought of as the set of all possible finite sequences of elements in set A. Because we often use characters instead of numbers with strings, we often refer to the loftily titled set of arbitrary symbols as an alphabet, and the set of all finite sequences of elements are called words or strings. For now, we can assume that A star also contains the empty sequence or empty string, which is denoted by a capital lambda. So, if A is the English alphabet, then A star contains all the words we know and love, like math, sequences, or educational. It also contains nonsense words, like synthenomicon, or even truly cryptic strings like this. Note: not all symbols in an alphabet need to be single letters. The alphabet Romeo Juliet meets, loves, dies, poisons, window is a completely legitimate alphabet, and strings created from it could be Juliet meets Romeo, Romeo loves Juliet, loves, 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 meets, dies, dies, dies. Just like how any given combination of letters may or may not be a real word, any given combination of words may or may not be a real sentence. Alphabets can have infinite combinations of symbols, most of which are completely useless to us. So to navigate alphabets, we can use regular expressions. A regular expression acts like a filter. Only combinations of symbols from the alphabet that create the pattern defined by the regular expression are allowed through the filter. To create these filters, there are 5 rules. First, the empty sequence is considered to be a regular expression. Regular expressions are defined recursively, so we need this for a base case. Second, if a symbol is in the alphabet, then it is a regular expression. So if our alphabet equals A, B, then both A and B are regular expressions. Third, if we have 2 regular expressions, their concatenation is also a regular expression. So our alphabet of A and B can define AB or BA by combining our symbols. AB and BA are also regular expressions, so they too can be combined with other regular expressions, including each other. This can continue to any arbitrary length. Fourthly, if we have 2 regular expressions, then their union is also a regular expression. So if our regular expression contains A union B, then symbols containing either A or B in that position will pass our regular expression. Finally, sometimes we want our regular expression to have the capacity to express certain infinite sequences. So if a symbol is a regular expression, then that symbol, followed by a star, is also a regular expression. So B star says at this point in our regular expression, accept any data from the empty sequence to an infinite number of B's. Let's look at an example of A, B star, A union B star. What this is defining is a regular expression that will let in any sequence that begins with 1A, then is followed by anything between 0 B's to some number of B's. The next symbol must be either A or B in any order or amount. So a sequence B, 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 B would fail because it doesn't begin with A. Meanwhile, A, B, B, A, B would succeed because it's an A followed by some number of B's, followed by some number of B's or A's. Feel free to pause the video and consider trying to make your own regular expression filters, or look in the video description for some other examples and try to figure out what sequences will pass the regular expression and which ones will fail. When our regular expression is applied to an alphabet, the strings that can pass through it are called a regular subset of A star. Regular subsets have 5 rules, each corresponding to a rule for regular expressions. First, if our regular expression only passes the empty sequence, then the regular subset is the set of the empty sequence. Second, if our regular expression passes a symbol from the alphabet, then that corresponds to the regular subset containing that symbol. Third, we can concatenate regular subsets to create a new regular subset. Formally, this is if alpha and beta are regular expressions corresponding to sets M and N of A star, then alpha beta corresponds to M dot N, which is the set S dot T, where S is in M and T is in N. What this is saying is when concatenating regular subsets, the new subset is every combination of one of the symbols in the first set matched with every symbol in the second set. Don't be confused by the notation. Fourthly, If alpha and beta correspond to subsets M and N, then the intersection of alpha and beta correspond to the union of M and N. Finally, if we use a star in our regular expression, the corresponding subset will contain an infinite number of finite strings starting at the empty string. Regular expressions and regular subsets have a number of direct uses when handling text-based data or in search engines. They also come up in automata theory because both regular expressions and finite automata define what are called regular languages. But that's a video for another time. Next, let's talk about arrays. Those of you familiar with computer programming might be looking at sequences with their lovely positional properties and think, that's an array. Sequences and arrays are different. An array can be thought of as a bunch of open boxes that can either be empty or full. An array of size 8 with nothing in it is the same array when we fill it. However, a sequence is defined by its values and their positions. So if we change a value, we have a completely new sequence. On that note, sets and sequences can be changed or typecast into each other. Any sequence, like 1, 2, 3, can become a set of its disparate elements. However, this is not always a reversible process. The set 1, 2, 3 could just as easily be the set 3, 2, 1. So when we convert from sequence to set, we give up the positional data of the sequence. Another quirk of typecasting a sequence to a set is that if we have a sequence, AB, 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 it becomes set AB, because sets remove duplicate values. That brings us to the characteristic function. From a very high level, this is a function that assigns some value to each element of a set. So if we have some universal set with subset A, then the characteristic function looks like this, where for any given x, this function returns 1 if x is in the set and returns 0 if x is not in the set. This is incredibly powerful because it lets us take the set math we've been working with and convert into numbers, which we can add, subtract, and multiply. This allows us to convert intersections, unions, and the symmetric difference into numerical formulas. Let's first look at the intersection and how it replicates multiplication. To do this, we'll use a table showing values of fa of x and fb of x. So when x is in A, we have a value of 1, and when x is not in A, we have a value of 0. Similarly, when x is in B, we have a 1, and when x is not in B, we have a 0. The only way to get 1 is if x is in A and x is in B. Otherwise, we have a 0, so our multiplication goes to 0. We can now calculate unions using the same chart, but we need addition as well as multiplication. We can use the formula fax plus fbx minus fax times fbx. If x is only in A, then the first part of the formula goes to 1 and the rest becomes 0, giving us a total of 1. So we know x is in A union B. Likewise, if x is only in B, the second part of the formula goes to 1 and the rest goes to 0. Now, if x is in both A and B, all three parts of the formula go to 1, and then it becomes 1 plus 1 minus 1, which is still 1. And finally, if x is in neither A or B, then everything goes to 0, and we know x is not in A union B. The symmetric difference is the same as the union, except we have to remove the intersection, so we multiply the final term by 2. If x is only in A, or x is only in B, then nothing changes, as the first or second parts of our formula go to 1, while the rest goes to 0. Similarly, if x is in neither set, the whole formula goes to 0. If x exists in the intersection, then the first two parts of our formula go to 1, and the last part of our formula becomes 2. 1 plus 1 minus 2 is 0, so we know that x is not in A, symmetric difference, B. Characteristic functions are extremely common throughout mathematics, and we'll talk a lot more about them later. For now, we can think of them as encoding set membership. So if we have a universal set, 1 through 8, and a few subsets, like A equals the prime numbers or B equals the even numbers, we can encode these subsets as bits of data. So A equals the sequence 0, 1, 1, 0, 1, 0, 1, 0, and B becomes the sequence 0, 1, 0, 1, 0, 1, 0, 1. We can now store a long array of integers, like 2, 3, 5, 7, as a binary sequence, which is the base 10 number 106. The last thing we'll talk about in this video is infinity. One property of sets and sequences is countability. If a set can be arranged into a list with a first element, second element, third element, and so on, then the set can be counted. So any finite set is considered countable. More interestingly, some infinite sets are also countable, such as the integers or the rational numbers. If we can't arrange a set in such a way, then we consider it to be uncountable. The real numbers are one such set because it's impossible for a sequence to encompass every real number. We can demonstrate this with a proof by contradiction. Imagine constructing a decimal between 0 and 1, using the form 0.A1, A2, A3, where AI is some value between 0 and 9. Then, we could create a sequence of such numbers. Now, let's create a number that isn't in our sequence, but has a similar form. To pick the first digit of our new decimal, we'll look at the first number in the first decimal in our sequence. If the number is 2, our new decimal will have a 1. Otherwise, it will have a 2. We'll then look at the second number in the second decimal, and that's how we'll build our second digit. By continuing this pattern into infinity, we can create a real number that could not have been in the sequence. This is called Cantor's diagonal argument, and it proves that infinity has different cardinalities. The cardinality of the natural numbers is less than the cardinality of the real numbers. This is important, because the output of a computer program often is a set or something that can be defined as a set, like we mentioned with regular expressions. Knowing that the output will always be countable, or maybe uncountable, can be the difference between letting a multi-billion-dollar server run on a problem for a month, or knowing to stop considering a program's output if it can't be made sense of in 8 seconds. In conclusion, sequences are sets with order. A single, simple property with massive implications. Order allows us to create strings with repeated characters, represent massive amounts of data with only zeros and ones, and even allows us to make concrete statements about the multifaceted nature of infinity. We're still a long way from capturing all the mathematics that go into a computer, but I want to congratulate you on taking the next step in your journey through discrete mathematics.